Hello and welcome back. In this video, we will be discussing limits at boundary points. So we're going to learn a little bit of topology in this video. Topology is a branch of mathematics that's concerned with surfaces and structures of sets, things like this. We're not going to get too far into the weeds with topology, but there are a couple of terms we need to pick up from that branch of mathematics to better understand sets in R2, because that's our domain that we're working with these functions of two variables, so we need to better understand them. Now, I want to motivate this discussion a little bit with by going back to Calc 1 ideas. So remember in the very last video, we calculated a limit of a function of two variables, and it was really easy. We did this by direct substitution. There wasn't really anything confusing going on with the function. The domain was all of, well, it wasn't all of the R2, but we weren't finding the limit at a weird point of the domain. Okay, so what am I talking about here? What exactly am I getting at? Well, let's jump back to Calc 1 for a second. So think about what was an interesting limit in Calc 1. It wasn't one of these where we could just do direct substitution, but one more like this, sine of x over x, and if we, say, wanted to calculate the limit as x went to 0 of this function, remember, this took some work. We had to use the squeeze lemma to calculate this, or L'Hopital's rule. If we had L'Hopital's rule, and we would find that this limit was 1. And the idea here was that we couldn't just use direct substitution, right? Direct substitution didn't work because we were evaluating the limit at a point outside of the domain, and not just outside the domain, but outside the domain at a point where anywhere around x equals 0 was a point in the domain. Right, a little bit weird. That is, our domain was all real numbers except for 0. That was the domain of our function. And so if we graph that domain, here I have the real number line, and I've just highlighted in blue what is part of the domain, right? So extending to negative infinity here, extending to positive infinity there, that's all part of the domain. But 0, here I've drawn an open circle around it because 0 is the only point not in the domain. So this is a special point of the domain. This point x equals 0, so it's not in the domain. However, it is a boundary point of the domain. So this is a boundary point of the domain. So it's a boundary point because any little open interval I draw around 0, no matter how small I get, any open interval around 0 contains a point in the domain and a point not in the domain, specifically 0, right? Think about any little open interval around 0, no matter how small you make it, as long as it's an open interval, contains 0, that's not in the domain, and it'll contain a point just a little bit bigger than 0, you know, 0.0001, however small you make it. There'll always be a point a little bit bigger than 0 and a point a little bit smaller than 0 that is in the domain. So no matter how small we make this, our open interval contains a point in the domain and a point not in the domain. That's what a boundary point is, and it made finding a limit as x went to 0, as we approach that boundary point, it made it quite an interesting problem. So that's what we really want to study. That's what we really want to study, are these sort of fringe cases, these boundary points of the domain. So a little bit more about boundary points before I get into two dimensions for our domain. Here I have the open interval, the set 3, 4. So that's an open interval, and here I have the set 3, 4 with brackets rather than parentheses, so this is a closed interval, right? Open interval, closed interval, we're familiar with those things. This is what it looks like with set builder notation. And then I've graphed these sets on the real number line. Again, for the open interval, right, I've drawn open circles around 3 and 4 because these are not in the domain. However, these are both boundary points, right? Imagine any open interval I draw around either 3 or 4 will contain a point not in the domain, so on the right side of 4, and a point in the domain on the left side of 4. So these are both boundary points. And then flip-flop that for 3, right? To the left of 3 are points not in the domain. To the right of 3, there are points in the domain. Boundary points. And what's important here is that the set 3, 4, it's open because it doesn't contain the boundary points. Does not contain its boundary points. Right, these are boundary points of the set. Compare that to the closed interval 3, 4. 3 and 4 are still boundary points. Again, imagine any little open interval around 3 is going to contain some points in the interior of this interval and some points on the exterior. And so again, 3 and 4, they're still boundary points of the set. But now the set 3, 4, it's closed because it contains its boundary points. So that's the idea. A set containing all of its boundary points is called closed. And when we're just dealing with the real numbers, so one dimension in our domain, that looks like a closed interval. And a set's open, well, I'll give that definition in a second. But this is the idea of open and closed intervals in terms of boundary points. So, right, this is what we want to study when we jump up to 2 dimensions. So here's our definitions. Thinking now in 2 dimensions, so functions of 2 variables, our domains are in R2. We define an interior point of the region. So, right, imagine some region in R2. Call it an interior point if it's possible to find a little disk around that point that contains only points of the region. So every little, or there's some little disk around that point that's entirely contained in the region. Now, a boundary point, as I just described in 1 dimension, is sort of on the edge of the region. It's on the edge in the sense that every disk centered at that point contains at least 1 point in the region and at least 1 point not in the region. We say a set's open if it consists entirely of interior points. And we say a set's closed if it contains all of its boundary points. So let me show you a couple examples here to get the hang of interior points, boundary points, open, and closed. And we'll do this in R2, which is where we'll be working domains of our functions of 2 variables. So let's take, for example, so here I am just in the plane. Here's a region in R2. All right, so we're working inside of R2 here. I'll just kind of close it off at some point, but here's all of R2, and here's my region R. So this is all, should be shaded in. This is my region R, is everything contained in here. So I'm just going to shade it in just so we know we're talking about the enclosed region as well as the boundary here, as well as the curve here, because I've done a solid line along the boundary rather than dotted line. That's how I'm going to differentiate between containing your enclosing curve and not containing it. So this, let's just talk about interior points and boundary points for regions in R2. So if I pick a point like, let's say here, actually I'm going to use a different color for that. Let me pick blue. So if I pick a point, say here, I can ask myself, does every little disk around this point contain points outside of the region and inside of the region? Or can I find a disk around it that contains only points inside of the region? Those are my 2 options. In this case, I can find a little disk around my point that contains only points inside of my region. And so this little point here, this is an interior point. And if you claim that you have an interior point, you should be able to find that disk around it that is entirely contained in the region. And so for this one, I could choose this disk. But a bigger disk would work as well. But I can't say pick a huge disk like this. That wouldn't quite work. Because then there'd be some points outside of the region and some points inside of the region. But this works to show that it's an interior point. Now, compare this to a point, say, let's go here, on this enclosing curve. Well, now, no matter how small I make a disk around this point, I could try that disk. Uh-oh, that one contains some points outside the region and some points inside the region, right? I could try making it smaller. But that's still not going to work because I'm right on the boundary, right? I'm right on the boundary of this region. And so there's no way I can draw a disk around the point to be entirely closed and enclosed in R, and so this is a boundary point. Now this region that I've drawn, is this a closed or open region? Remember, open means it consists entirely of interior points. Every point in the region is an interior point. Closed means it contains all of its boundary points. So the only boundary points for this set are the ones that are enclosing the region. So all of these around the region, these are boundary points. And I've drawn a solid line here, which means the region includes those. So this is an example of a closed region. It's not open because it contains some points that are boundary points. So let's take a look at what's an example of an open region. So I'm going to define a set here. Let's say all x, y in R2 in the plane, such that, let's say, x squared plus y squared is strictly less than 1. All right, what does this look like? This looks like a circle. Maybe I should draw some axes here. Just freehand it. So here's x and y. And let's say this is 1. So here's my region in this problem, or for this set. This is my set. This is my region R. I've actually made a mistake already. I'm going to jump back. Notice I drew a solid line around it. Why did I do that? Well, I shouldn't have, because this is all x squared plus y squared is strictly less than 1. So if this is 1 here, 1, 1, negative 1, negative 1, I don't, my set actually doesn't contain those points. Oh, jeez. My set actually doesn't contain those points. I better do it like this. 1, 1, negative 1. So I should do a dotted line. Don't contain those points. But everything inside is part of my region, right? So all the inside is there. All right, so now I can ask myself about boundary points and interior points. So something like the origin or over here, these would both be still interior points. These are interior. So it still contains a lot of interior points. Let's ask about boundary points. So we still have boundary points along this enclosing curve, the unit circle. So there's a boundary point here. But the difference here is that my set doesn't contain its boundary points. Again, the boundary points are found along the outside, right? It's this enclosing curve, the unit circle is all of the boundary points, but my set doesn't contain those. So what this means is my set consists entirely of interior points. So this is an open set in R2. How about another closed set? So if I were to do x squared plus y squared less than or equal to 1, so if I do something like that, xy in R2, such that x squared plus y squared is less than or equal to 1, then this is another unit disk, right? So this, we call this one up here, this is the open, oops, let me scroll up a little bit. This is an open unit disk. So open because it's an open set, unit disk because it's of radius 1. Right? Unit really is really means 1, a synonym for oneness. If I do something like x squared plus y squared less than or equal to 1, well, now I'm including that set of boundary points. So my set looks something like this. Now it's a solid line on the outside, and I have all of these interior points as well. This would be closed because now it contains all of its boundary points. So this is what's called a closed unit disk. All right. I think this is really what we need. to talk about limits now. So I think I'll end this here. I do want to talk a little bit more about open and closed regions. It's not strictly necessary for this video. So I think I'm going to do it as like an extra video. I'm going to talk about open and closed regions because this idea of open and closed, just because a set is not open doesn't mean that it's closed. And just because it's not closed doesn't mean that it's open. You can have sets that are both open and closed, or sets that are neither open nor closed. All of those possibilities can exist, and so this is really sort of bad nomenclature to call these open and closed. That implies they're opposites. They're not really opposites of each other like they are in one dimension. When we get this extra dimension, weird things can happen. So that's, I'll call that good for our discussion here of boundary points and interior points. This will be helpful. There's other sort of sets we can encounter. So for instance, in the next video, we're going to work through some examples of evaluating limits at boundary points. So like this one, we can maybe make this denominator 0 in such a way. And so its domain is going to look something like this. It's going to be all the real numbers except for a line. So it's like we just remove a line from the real numbers. We're going to have a set that looks like that. And then we could also have a set like this one. It'll turn out the domain of this is just, we can't have x and y both be 0. So it's the whole of the plane except for the point 0, 0. And that's just the whole plane, removing the origin there. So we're going to be evaluating these two limits at boundary points that are not in the domain. All right, I'll see you next time, and we'll work through this limit.